Hello. I wondered what would happen if we had a situation like here a 9-volt battery, and this is connected to a resistor, and let's say this resistor has 1 kilo ohm, and then you would calculate via the standard Ohm's law U equals R times I. And that is then I equals U divided by R, which is 9 volt, the whole 9 volt over the resistor over 1K. And this is 9 divided by 1000, 9 milliampere. So quite straightforward. So 9 milliampere is flowing through this resistor in that scenario. Here the 9 volt is a standard battery you can buy. But also what you can buy is a 1.5 volt AA battery. And what if we connected this in the same direction as the 9 volts? So we do it here like this, and then like this. So let's connect it here and here. And what is happening now? I mean, the fact is that we have here, this point is connected to both of the negative poles of the batteries, and they have a common ground. So they are referenced to the same ground potential here. And different things could happen. Perhaps one thing that could happen is that I have here 9 volt compared to a common ground, and that I have here 1.5 volt compared to a common ground, and that this 9 volt produces, this is more positive. So this could produce a current flowing through here and then in here, or it could happen that the 9 volt I produce a current flowing through here and then somehow over here, and then this would be kind of a short, this outer circle or this outer network, and perhaps no current is going through this 1 kilo ohm resistor at all. And I don't really want to connect this in this manner because I'm risking here producing a short and I don't know what happens to my batteries. I don't know. Perhaps what could be a kind of cool way to try this out, but not to break stuff in an unpleasant manner. Perhaps if I put something of a safety resistor in here, I mean, this is 9 volt, and then go here, and then we would have 7.5 volt, because if this 1.5 volt is in the opposite orientation, so we would be left here with 7.5 volt. And then what could be also is, because these two are parallel, so this 1.5 volt and this 1 kilo ohm, it could also be that here are 7.5 volt and here are 7.5 volt, and that. So what I think I'll try is first to put a resistor in here. Perhaps we'll go to the European version of resistors. So perhaps we put a resistor here, 1 kilo ohm. Now this looks like something. Okay. And then if we would have 7.5 volt in this branch and 7.5 volts in this branch, then there would be here kilo ohm and here kilo ohm, and there would flow, like I said in the beginning, with the 1 millivolt, with the 9 millivolt calculation, there would be flowing here 7.5 milliamperes. Like, let's enlarge this one. here 7.5 milliamperes, and they're probably flowing here 7.5 milliamperes. If we had such a constellation, we could say, okay, it cannot be that the current is flowing from here to there and then in here again, because if this both are 7.5 milliampere, this would mean that there had to be a 7.5 volt drop across here, and then another 7.5 volt drop across here, which means in sum on that path, drop of 7.5, another drop of 7.5 from here positive to ground, and that means 15 volt of drop. And we have not 15 volts available anyway, so even if we added 9 volts and added 15 volt, 9 volt and added 1.5 volt, we would get only to 10.5 volt, but never the 15 volt here. So that cannot then be that the current is going this way. So how else could this these 7.5 exist? So yeah, basically when we have 7.5 milliampere over this resistor here in the middle, then that's a drop of 7.5 volt. All that there cannot be 7.5 volt left anyhow. So if we have 7.5 milliampere here over this 1 kilo ohm resistor, then we can be pretty sure that is because of the 9 volt here, and then the 1.5 volt opposition to the 9 volt, and then 7.5 across both of these branches. Then, but let's see. Let's go to reality and let's see what really is happening here in reality on the breadboard. So, and here we are. This is my 9 volt adapter. I'm connecting it to the breadboard, to the upper rails. You have a plus and minus rail up here in the breadboard, minus blue, plus red. And yeah, we have a 9 volt battery also here. Quite good. I know that it's very well above 9 volt, so 9.5 the last time I checked it. Not used much, should still be very stable. And yeah, that is brown 1, black 0, so 100, and then another brown to the left, which is 1000. I had to put the plus pole over the resistor. Here we connect the plus pole. Here I have such a case for 1.5 volt battery with connectors. Connect that to the lower power rail connection here. Let's try it again. So we had here plus in the 9 volts, then over resistor, then here, then the 1.5 volt pointing, and then another kilo ohm resistor and connecting the two here at the bottom. And so what we have here is now the 9 volt. They are here, and then we connect the positive rail to the resistor. We have to connect the 1.5 volt top thing plus pole also to the resistor. Let's do that. Some sort of, we connect this here to the other positive rail, going through. We can connect then here. Then we said we wanted to have another 1000 ohm resistor. Oh, what is this? This is, hope you see it. It's brown to the right, then black, brown. That's exactly what we want. And then we have to connect
minus of the 1.5 via resistor to the other resistor end down here to the other resistors far end. So we're set up this way, and then the last thing we do is to set this joint, to connect this joint to the ground of the 9-volt battery. We connect that to the ground of that, and we're all set. So we can either measure now the current that is going through these resistors, or we measure the drop. I mean, a drop of, let's say, 7.5 volt across the resistor would mean 7.5 milliampere. So how that's the specialty of a 1K resistor. So no matter how many, so let's say you measure X volt drop across the resistor with your meter, and you know, okay, there are X milliampere flowing through the thing. You can put it here to see nicely. Put it to measuring volts. Put it across the middle one. Let's say here. Yeah. Good thing. Now we start connecting the batteries. Famous last words. Oh, already we have 0.7. So yeah, the current is flowing, as you might have already guessed. When I only collect the 1.5 volt battery, it starts flowing from here over this resistor, and then each resistor drops because we're not connected to any 9-volt battery here. This is always open here to the right, and then you have a simple 1.5 battery with a circuit of 2 1K resistors, and every 1K resistor drops half the voltage of the 1.5, so about 0.727, because the battery is not perfect 1.5. The battery is around 1.4 something, 1.45, as you might guess here. So that's exactly half. Okay, now interesting. And now what happens if we digital multimeter? Here you see I connect the battery. All in the picture, good. And let's connect it. And now there is a pure 9.5 volt drop. That's nearly exactly what the bigger battery is. That's interesting. And then let's switch the other resistor. Okay, we can keep the ground at this position, but move to the other resistor. And there is a 8.8 volt drop here. Okay. And 9 point. Okay. So this is because of the real values. We have not a 9 volt and not a 1.5 volt battery, but we have a 9.5 volt battery. Here, this one is 9.5 volt. And this one, the smaller one, is 1.4, so to say. And so if you subtract from the 9.5 this 1.4, so roughly you end at 8 volt. And I think, so the numbers are not like we expected, because we calculated with EDL 9 volt and EDL 1.5 volt. But if we take into account the real values of our batteries, which I can measure for proof, 9.5 volt, and the small cell is 1.457. This seems to me like we've made a perfect guess, dropping the whole 9.5. But that's interesting. The opposition to the voltage is only in the branch where the battery really is. So the whole 9.5 volts, they drop over the two branches equally, but on the only, so this we have over the 1 kilo ohm resistor in the middle. Here in the middle we have the whole 9 volts of the battery, and only in the branch where this 1.5 volt battery is, we have a drop of less on the resistor, so a drop of 1.45 less. So this battery only is doing something against the voltage of the battery in its own branch here to the left, and not in the whole parallel circuit. Okay, and so we have in this branch where the battery takes an effect, we have roughly 8 volts or 7.96 volts. And it's the same direction of current as you see here, the ground and the positive probe. And we drop voltage towards that point where these two join to the grounds. This means that my initial suspicion could be right. If I would only have in a circuit with the 1.5 volt battery, if I would do out the resistor, there would much certainly be some kind of short here. And that is very interesting. This means that current is flowing through this battery here in the opposite direction. So really it is as if this 1.5 volt battery isn't here. Once you subtract the 1.5 volt of it from the 9 volt battery, it's as if it's a short, but only with 1.5 volt less. And I think I'll make another part of the video where we do exactly that, where we put them two in the row in opposition and see what's happening. But now let's return to the board.
So what we've seen is that these 9 volts, they are dropped as a whole over this central, these 9 volts, they are dropped as a whole over this central kilo ohm resistor. So you have the same amount of voltage in general over the two parallel paths. But here over the right 1 kilo ohm resistor, you have the whole 9 volt. And therefore, you have, we didn't measure current, but if you would measure current, you would have here, with these EDL values, you would have here the 9 milliampere over the 1 kilo ohm resistor. And really in our ideal world, yes, you would have these 7.5 milliampere, because what's happening only in this branch is you have the whole 9 volt here, and you subtract this 1.5, so you're left with 7.5, and then you have over this 1 kilo ohm the 7.5 volt that are left, and then you have 7.5 milliampere, and that's really what's happening here. And that is good. I hope you liked it, and I think, okay, never seen it that way. But what I can also do, and what I'll try out now, is, so let me erase that for a moment. And now we could do a second thought experiment, very related. So let's say we have here this 9 volt battery, and then immediately, so let's say here, here's the plus, and then if you put in opposition the 1.5 volt battery, and if we can leave it that way, and if we measure here this situation, that would be the first thing we do. We measure if this is really 9 minus 1.1, 1.5. So first thing we measure is if we are here left with around 7.5, so the subtraction of the two. That is the first question we answer then next in practical. And then the next thing will be, if we connected then this pole here through a resistor, 2 of, again, let's say 1 kilo ohm, Do we really drop also then the 7.5 volt across here? Which would mean, because in a resistor, no voltage drop without current, and no current without voltage drop. And if we drop the 7.5 volt also over the resistor, this would mean we have a current flowing here of 7.5 milliampere. And 7.5 volt over a 1K resistor, this would be 7.5 milliampere. And this would answer the question of, yes, although the technical direction of current is from plus to minus, it would be as if this battery would not be here and only subtract 1.5. And virtually here would be technical current flowing from here to here. This would be very interesting. And now let's do this practically on the breadboard.
Okay, just a quick reminder, we want to create this situation. 9 volt against the 1.5 volt. And the first thing we want to measure is here in reference to this point here, are we measuring 7.5 volts here? Question mark. And for this, let's have our digital multimeter. We wanted to connect, so first of all, this battery minus plus the 9 volt, it's the primary. And then against it, we set the plus, so the red plus of the 1.5, we set against it here, zack. And as you see, I hope you see good, these two are now connected to each other. And then we put the reference here, zack. And yeah, just to measure that, we stick in some wire on the negative of the 1.5 and the negative of the 9 volt. And here my cat is joining the party. Hello. And let's see. So the negative of the 9 volt. And now we connect here red one. 7.95. So really interesting what we expected. Also again, it's not 9 versus minus 1.5, but it's 9.5 minus 1.5. So to speak, roughly rounded the real values. And so we come out at 8 around and not around 7.5. But with these real values, it's exactly the way we imagined it to be. And now let's do one last thing. Let us connect a resistor. This 1 kilo ohm resistor still over the 7.5 volt. And we can see that so the voltage must be here. Oh no, it must be lower here, and then from here to here. Yeah, and we're dropping the 7.92 volts in the measurement range. It's exact. So cool. We can still do, if you don't believe me that there's a current flowing here, we can still do something different. My cat is now going crazy, but that's no. Yeah, so we can set this meter here to measure milliampere. Let's set it to the milliampere range. And then if I just switch out these test leads here. So yeah, this is standard lab equipment. I think this is, I don't know, 4 millimeter standard. And if we then, yeah, these nice little ones, they easily go then into the breadboard because the tip is so pointy. It's really cool to measure on breadboards with these, and we exchange those here. Have these nice connector plugs. Oh, they're suitable for 1000 watts. Who needs that? But okay. So now let's see. Let's not measure voltage now. Let's measure real current between here. So if you measure current, you really make the connection with the digital multimeter. Always a cool thing. You make the connection and yeah, 7.99 milliampere. And this means exactly what we expected with our 7.9 volt drop of the 1 kilo ohm resistor. Exactly within measurement accuracy and everything. So thank you for watching. This was quite cool. Hope you liked it. Please like and subscribe, and see you at the next video.